Hi, it's Mr. Anderson, and today I'm going to talk about solubility. To understand what solubility is, you first have to understand what a solution is. And so if you haven't watched that podcast, make sure you step back and do that. But solubility is a measure of how easy it is for a solute, in this case it would be table salt, to dissolve in a solvent. In this case it would just be water. And so the way that water dissolves a solvent, remember, or a solute, is that it'll actually surround the anions and cations inside that salt water. But solubility is a measure of how good it is at actually doing that. And so it's going to depend on what you're actually trying to dissolve. And so right here we've got a picture of a solute. We'll call that a solute sitting inside something that looks like a salt shaker. And then we've got solvent. And so in this case the solvent is going to be exactly 100 milliliters of H2O. And so if you look at this value over here, the solubility value for each of the different solvents is going to be a little bit different. And so the solubility value for salt is going to be 37.7. And so that means at room temperature, if you take 100 milliliters of water, you're going to be able to dissolve about 37.7 grams of table salt. Now if we compare that to sugar, you'll find that the solubility value is going to be much higher. Sugar, or sucrose, is going to have all these hydroxyl groups around the outside. So you can actually take 200 grams of sugar and you can dissolve that in 100 milliliters of water, which is an astronomical amount. So you can get a huge amount of sugar mixed inside there. It has a high solubility value. If we compare that to something like baking soda, it actually has a value of around 10. And so it's hard to get baking soda actually to dissolve in water, and a lot of that has to do with chemistry. Remember, water is going to be a polar molecule, so it's really good at things that breaking down things that are charged. If we get something that's not charged at all, let's say talcum powder, you could try and mix it with water day and night, and you're never going to get it to mix together. And so if it's not able to mix, we call that insoluble. In other words, it has no solubility value because it doesn't matter how much you add to it, water's never going to make a solution out of it. So we call that a low solubility value. Now, if I want to add more solute to water, one way that I can get more added to it is I can actually increase the temperature. And so this solubility curve actually has temperature on the bottom, goes from 20 degrees all the way up to boiling, 100 degrees on this side. And then on this side it's got the solubility values. So solubility values, which is the grams of solute for 100 grams of water. And you'll see that there's going to be a curve for each of the different salts. Now why is it that if we heat up water it's able to dissolve material better? Remember, the way temperature works is that temperature is essentially how fast the molecules are moving around. And if they're moving around more quickly, they're more readily able to surround that salt. But it's not always exactly the way you might think. And so if we look at something, for example, here like potassium nitrate, you'll find that its solubility value down here at a really cold temperature is actually around 30 grams, but as we get it way up to near boiling, we can get that number up near 200. And so that makes sense. But if you look at some things, like here's sodium chloride, so that's just regular table salt, you'll find that its solubility curve is actually relatively flat. And that means that if you heat up water, you're not going to be able to dissolve much more salt. There's kind of a limit to that. And so that's dissolving solids or solutes in water. So what is saturation? Saturation is a measure of the point at which we reach where you can't dissolve any more solutes inside it. And so in this picture right here we've got two phases, which is pretty cool. Up here we've got actually the phase between this sugar solution and the air. And so there's going to be movement, and so each of these particles that is a hollow circle with an arrow attached to it is going to be gas. We could think of that as like oxygen or nitrogen or air. And so that's going to be moving into and out of solution. In other words, some of it's going to be moving out into the atmosphere and some of it's actually going to be dissolved inside the liquid. And then at the bottom we've got some sugar cubes in here, and some of that sugar is actually becoming into solution and some of it is moving out of solution. And so the point at which we reach a saturation level, it means that we've added the most. And so let's just kind of think about this area down here. We've got sugar that we've added to it. And so up here we have an aqueous sugar solution. So it's sugar water. And so we have so much sugar down here in the bottom that eventually you get to a saturated point. It's the point at which you can't have any more sugar enter into the solution. Now, it doesn't mean that no more sugar is moving across. It means that it's reached this equilibrium when the movement into and out of solution is actually equal. And so when it does that, we reach something called a saturated solution. And so unsaturated is when we could actually add more to it. Saturated means you can't add any more to it. So you might be thinking to yourself, well, I understand what saturated is, but what is supersaturated? How could I ever add more solvent to the, or solute to the solvent than can actually fit? And so you have to think back to the slide before this, and that was, remember, we can actually increase the temperature, and if we increase the temperature, we can add more solute to it. And so you can imagine if I increase the amount of heat, I can actually get more solute to absorb into the solvent. And so this is a pretty cool demonstration. What they've done here is they've taken sodium acetate, they added it to water, and they made a sodium acetate solution, but then they heated it up, so they got it really, really hot, and they were able to add more and more and more of that solute. It then became supersaturated when they let it cool down. In other words, there's more solute in here than it should be able to dissolve. And so the cool thing is you can add a crystal, and if you add a crystal of sodium acetate, you'll get this beautiful crystals forming, and eventually all that's going to come out of solution again. So it's going to go back to a saturated point where it's at equilibrium. Now, what's a fun way that we can actually play around with supersaturation? That's how we make rock candy. And so what you do is you heat up water, you get sugar to dissolve inside it, and then you cool it down, and we can put something like a stick or a string inside it, and then if you let it sit long enough, it'll actually crystallize. And so that's a supersaturated solution, but we're getting those solutes to come out of solution over time. Next one is gases, and gases kind of flows in the opposite direction. And so remember, in a solution, let's say carbonated water, what you have is water, and then there's carbonation, or there's going to be carbon dioxide gas that's actually absorbed into it. So it's little bubbles inside there. Now this works a little bit differently. If you remember back when we were talking about solutes, as we increase the temperature, we were actually able to absorb more of those solutes into solution. Gases work in the opposite direction. As we heat up water, you can actually hold less of that inside there. What's an example of this? Well, there's a really good life example of this. And so this is a Elodea plant. But essentially what's going on is that this plant is putting oxygen bubbles into the water. And the amount of water that you get, the amount of oxygen that you get inside the water is called the dissolved oxygen rate. And so if you have a fish tank like this, and it's got a fish inside it, what's the fish actually breathing? The fish is actually breathing dissolved oxygen. So it's not breathing, for example, the H2O that is sitting inside the tank. Let's get a little bit of water in here. It's actually breathing the oxygen that is dissolving. So it's the oxygen from the atmosphere that's actually dissolving inside here. And so how do you get more oxygen in there for your fish? Well, you could put a bubbler in your aquarium if you ever had one of those. And what that's going to do is it's actually going to add air, and it's going to add bubbles to the water, and so it's going to increase the amount of dissolved oxygen. The problem is this: as we heat it up and we get hotter and hotter and hotter, the water can actually carry less of that dissolved oxygen. And so as you get hotter and hotter and hotter, you have this problem. You have one of all, the fish, and as you heat up the water inside the tank, the fish's metabolism is actually going to speed up. And the other problem you have is when it gets hotter and hotter and hotter, it can't carry as much dissolved oxygen. And so where do we see this as a problem? Well, you could see it around the globe. And so lots of times we tend to think that the most lush areas on the planet are going to be those right near the equator in the ocean. But actually, if you look at the dissolved oxygen levels, we're going to have way less oxygen here. And so where do you see the most life in the ocean? You see the most life in the ocean where you have cool temperatures coming from the south, and then you have enough sunlight at the equator. So we visit the Galapagos Islands, which are right here, and it's a great place because you get this cold current coming up from the south, which is actually carrying a lot of oxygen. It's also carrying nutrients with it, and then you get a lot of light up here as well. Where can this be detrimental? Well, let's say you build your power station right next to the ocean, And one way to get rid of that extra heat is actually to use the water from the ocean to cool it. This is actually a power plant that's located near San Francisco. As you pump that water back into the ocean, it's increasing the temperature, so it's decreasing the dissolved oxygen level, and it's really hard for fish and marine life that live right around that area, because not only are they speeding up their metabolism, but there's not enough dissolved oxygen for them to actually respire. So that's a double trouble. And so that's solubility. Again, a measure of how easy it is for solutes to be measured in solution. Thanks.